Next concept is that is magnetic field due to, or you can write, force between parallel current carrying conductor. Force between parallel current carrying conductor. Yes. So what you have to study, what we have to understand here, there we have to calculate the force that is between the two parallel current carrying conductors. Yes. So while discussing this chapter, in the beginning, we have discussed that if a charge is flowing through any wire, it will induce a magnetic field. And after that, we have derived an equation for a current carrying conductor which is placed in a magnetic field. For that, we have got an equation that V is equal to IVL sin theta. So by considering these two concepts, the scientists have thought that if the two conductors are placed placed parallel at a very less distance, they would apply the force on each other. This was the idea of the scientists from the previous concepts. So on this, Ampere was worked a lot, and they have tried to find out the forces between the two parallel current carrying conductors. That is this concept. Yeah. So to explain this, what we have to do is we need parallel current carrying conductor. We need the two conductors. It should be straight and parallel. Okay. Let me take two conductors. This is the one conductor. Let me take another conductor. They have uniform cross section. They have a uniform cross section. So let's say there is a current flowing through this conductor is IA. Through this there is a current IB flowing through it. Now, and these two conductors are separated by distance, very small distance, that is a D. Now, our intention is to find the force acted by these two parallel conductors on each other. That is what we have to find out here. Now, to do this, let's take a small element here, element of this conductor. Here to here, let me say the length of this is here. L is the length of this. Okay. Now, as the current IA flows through this, it will produce the magnetic field. Okay. As the current which flows through this conductor, it will also produce a magnetic field. Okay. What will be the direction? Then what you have to do is you have to apply the right hand rule. If you hold the right hand like this, if you hold the object in your right hand, the thumb represents the direction of current, this curved fingers represents the direction of magnetic field. It will be like this. So now you have to find the magnetic field due to this element on this conductor on the length L. You have to find out magnetic field on L due to this. Let me draw the direction of magnetic field. How to draw? I told you. Direction of magnetic field will be like this. This is the direction of magnetic field. Let me draw this very close so that I can clearly draw the picture. Okay. Now you have to take like this. Direction of magnetic field will be like this. Okay. So this is the direction of magnetic field. At this point, direction of magnetic field is downward. How to find direction of magnetic field is drawing the tangents to the magnetic field lines. Okay, this is the magnetic field lines. By drawing a tangent to it, it represents the direction. Direction of magnetic field at that point. So at this point, direction of magnetic field is like this. So here the current is flowing. Now what you have to find out is, we have to find out the magnetic field. Yeah. Now see here. Here, at this point, direction of magnetic field is, which is inward to this, current is flowing like this. So here the direction between this current element and the direction of B are perpendicular. See here, element is like this. What I can say, for example, these are the two conductors. So here you have to apply the rule. So direction of magnetic field here will be downward. Now what you have to do is, this is the direction of magnetic field. This is a conductor A, IA current is flowing through it. Now, this is the direction of current, magnetic field is downward. That means what is the angle from here? It is 90 degree. So the angle between that current element, current carrying element and magnetic field are 90 degrees. That is why we are able to apply Fleming's left angle. This is the rule we can apply. When the charged charges are moving perpendicular to the direction of magnetic field. Okay, how to apply? See here. This is the direction of magnetic field. So here, forefinger represents the direction of magnetic field, and middle finger represents the direction of charged particle, and thumb represents the direction of force acting upon this charged particle. So this is the direction of magnetic field which is inside. This is the direction of a current like this. So this is the direction of force acting upon this due to this. So it will be directed towards this element. So let me draw. At this point, direction of F on B, this one, on B, due to which one? A, F, B, which is directed towards this. Similarly, let us take the same length of element here also, that is here, and let us find the magnetic field on this element due to this conductor. Again, what you have to do is, again you have to apply the right hand rule, so that magnetic field lines will be like this way. So let me draw it in, I'm going to look like this. Magnetic field lines are like this. See, this is the loop. So this is the direction like this. So at this point, direction of magnetic field will be downwards. Then direction of field is downward. Then the current is flowing like this. So if you apply this rule, see here, this is the direction of magnetic field. Magnetic field. At this point, direction of magnetic field is like this. Yeah, current is right. Yeah, direction is like this. See here. If I take direction is like this, this is the direction. Okay, this is the direction. So the direction of magnetic field will be like this. B is the direction of magnetic field above. So direction of magnetic field is above, coming out of this plane. This is the direction of current here. This is the direction of magnetic field. So this is force on A due to the F plane. So look at the directions of F. They are directed towards each other. That means these two forces are attracting each other. Okay. So from this, what you can understand is if the two currents are flowing in the same direction, then there is an attractive force between the these two conductors because of the magnetic fields. So let's derive the equation. Now, before that, let us write the equation for magnetic field due to A on magnetic field produced by conductor A. A on L is, that is from Ampere's law. From Ampere's law. What is the length? That is L there. BL, B dot EL, BL is equal to sorry, mu naught times, that is a magnetic field produced by this element, this one, current going through this, current enclosed by that element, this element, that is a IA. BL is equal to mu naught times IA. Sorry, this is a Ampere loop you have to take here. This is the Ampere loop here. So the length of this Ampere loop is at 2 pi d. D is the distance from the center. So here I have to write B times 2 pi d. So B gives mu naught times IA. IA means it is the current enclosed through the element, that is A. Mu naught IA divided by on L and on L 2 pi, that is BA. Is the BA right? Magnetic field by conductor A. That is the magnetic field A. Similarly, you can find out, you can apply the same Ampere's law, you can follow the same procedure, you can find out the magnetic field due to conductor B. Similarly, field due to B is equal to mu naught times IB divided by 2 pi d, because they are separated by distance d. Mu naught IB divided by 2 pi d. Let me take this is the equation number 1 and 2. Now we got the equation for field due to these two conductors. Now what we have to find out is, we have to find out the force on this due to this conductor, as well as force on this conductor. Force on B due to A is FB. Then force on B due to AT is given by A is given by, let me write here. Now we have to make use of the equation, that is F is equal to ILB sin theta. That is the equation we have to use. What you are finding? That is a force on B due to A. Force on B due to A. Equation what we are going to use here is ILB sin theta. F is equal to ILB sin theta. Let's say theta is the 90 degree. Okay, it is angle between L and B. Length and B, always 90 degree. Theta is 90. ILB. I means it is a current flowing through that conductor. So which is the conductor? Force on which conductor? This one. Force due to what? Conductor A. That means which will produces the magnetic field? This conductor will produce the magnetic field on this one. So what is the current flowing here? That is IB. ILB. IB. Then on what length you are finding? That is L. On L you are finding. L. Then B means magnetic field. I means it is the current through this conductor. Magnetic field produced by another one. This one. So magnetic field produced by this one. So that is why we have to write B. So let's substitute IB L into BA is equal to mu naught times IA divided by 2 pi d. So mu naught times L into IAIB divided by 2 pi d. This is the equation for force on B due to. Similarly, force on A due to B is, you have to follow the same procedure and you can write FAB is equal to mu naught L into IB divided by 2 pi. Okay, 2 pi d. So from if you look at the figure, what we can see is they are directed each other. The direction of these forces directed towards each other. Hence they are directed each other. That is why what we can write is FAB is equal to minus FBA. Okay, they are equal in magnitude, they are directed each other. So this is the result that we can write using the Newton's law, that is FAB is equal to minus FBA. So this is the result we will get here. So from this what we can understand is, if the two currents are going in the same directions, then the conductors will attract each other. If the currents are going opposite directions, then the two conductors will repel each other. So this is what we can understand from this concept. Yes. So FAB is equal to minus FBAB. So this is equal to Z, the forces are attracting forces. Yes. So here we got the equation for force, that is F. F is equal to, equation is mu naught L into IB divided by 2 pi d. Using this equation, we can define the definition for ampere. We already know that ampere means it is a unit for current. So the unit of that current can be defined using this equation. If you substitute L is equal to 1, L means length, right? D means distance. So if you substitute L and D as a 1, and let's say 1 ampere of current is going through it, then what we can say is the current flowing through the two parallel straight conductor is 1 ampere. 1 ampere of current will flow through both the conductors when the length of the conductor is 1 meter and they are separated by 1 meter of distance. Then they will attract the force of 2 into 10 to the power minus 7 Newton per meter to the power minus. Then that is called as a 1 ampere. Let me repeat once again. Let's put L is equal to 1 there. Length of the element is 1 meter. Distance between the two conductors is 1 meter. Current flowing that means 1 ampere. We can say that current flowing through the conductor is 1 ampere when the length of the conductor is 1 meter and the two parallel straight conductors separated by a distance of 1 meter. Then they attract with the force of 2 into 10 to the power minus 7. Newton per meter to the power minus 1.